Oh, hi everyone. Yeah. So my name is Shan, and I'm from Visa Research. And yeah, this work is done between me and all my colleagues, Rahul, Yizhen, Anderson, and Yiwei. So I'm going to talk about our work, which is trying to build a secure and privacy-preserving WFL framework. Okay, good. So yeah, so the FL actually is not a new thing. So for someone, if you are not that familiar with, so FL is just trying to build a learning framework where the multiple clients, they can collaboratively train a model while ensuring that their data remains decentralized. I'm like showing this figure. So WFL, actually, the vertical FL is a special case in FL, which that they assume that the client that they share the same samples, but each of them hold the different features, like the in this figure that all the part A and part B, like the client A and client B, that they share data from the same sample space, but each of them hold the individual feature space. And yeah, so typically the WFL can be defined that in such kind of formula, I mean, as a sys model. So it's trying to solve a minimum optimization problem, and there is too much notation, so I just pick some key point here, so that here L is just a task loss. And the capital theta just a joint model which can be decomposed into a global model, which we parameterize it by theta, and also the local models. And each of them that can be represented by a phi I, and here I is from 1 to capital N, which is the number of clients. So as we in WFL, we assume that each client just hold a subspace of features and denoted by the Xij. And normally we assume there are one client that it also will hold the feature. No, sorry, the label. So we call the client which has both the features and label. We call it active client. And for those who only hold the features, we call it a passive client. And so I will still keep it here. Yeah. So before we talk about the privacy-preserving WFL, let's talk about what typically like under the plain text scenario. The plain text here means no privacy-preserving, no secure computation. So how will WFL is running? So so the workflow is still pretty straightforward. That for each client, they just upload its intermittent output to a client, and the client pass them into a global model, so we get the final nodges. Then we just compute the gradients, and then we use these gradients to update the global model. So and to update the local model is the same thing. But here is one thing that because that the intermediate outputs are just passed to the clients. So in order to compute the G phi I, let's say the gradient for the local models, we need to use the chain rule, right? I think most of you are familiar with. So that means we will compute it by G phi I by dl over dh, multiply the dh over the d phi I. Here the h just the h superscript to I means the intermediate output for the ith client. So this is pretty straightforward, but you can find that without any privacy preserving, so both input and output privacy can be easily leaked. So for the input privacy means that the intermediate outputs uploaded to the clients are completely disclosed to the server. And the same thing, when we compute that the G phi I, the server will first compute the DL over DH and send them back to each client and per samples. So means that for those information sent back to each client, the client can easily, actually not that easy, but just if you're using some attack method, you can extract the information about the labels and the features from other clients from the DL or DH, which that the client I assume that he should not know this. So of course, there are already some works focused on both input and output privacy preserving in the WFL. So for the input privacy preserving, typically we just apply the cryptographic techniques like the MPC or HE, and on the WFL learning framework, and there are already many methods have been proposed. But the one problem here is that those guys only just consider the input privacy, so they didn't consider the output privacy preserving. And for the output privacy preserving, typically it's just we apply the DP, differential privacy, for preventing the output privacy leakage, like the conducted by the membership inference attacks, the MIAs. So there are also some works, several works have been proposed, but they are suffer from some limitations. Like for the ADML, it considers that there are multiple head, in the servers, so they consider that there would be a update of the multiple head and the local models, and but it will incur that the communication cost here is huge, and also it requires synchronize the randomness across all clients, and which I will talk it later why this could be a problem. And another one also proposed, they call it a dynamic noise injection, trying to find a good balance between the privacy and also utility trade-off. But this also has the issue that its computing cost is huge, and also actually its performance, which is also not that good. I will show it later in the experiment result. And there is also some work trying to combine both the input and output privacy. They just apply the local differential privacy on a very special case in WFL. It's called the fuzzy WFL. And it works good only because that under the fuzzy WFL, it has a one-to-many fuzzy linkage, so they can apply the subsampling, which I will talk it later. But if we consider a more general case in the conventional WFL, the subsampling will not work here if just based on their approach. So that's our goal. We're trying to build a general WFL setting, combine both the input and the output privacy preserving, and to achieving a better utility and privacy trade-off. So our theory model, we consider that we have 3 servers and for MPC, and they are both semi-honest and honest majority. And we also consider that we make a black box use all the standard MPC blocks. And all the clients we consider are semi-honest means that we will work, correctly on the protocols, but they will try to infer all the information, from both the servers and other clients. And we also consider there would be the external adversary. They can observe that, like the prediction outputs, that the gradients released, or even once the model is trained, we will deploy it online that they can query it, at any time. So we claim that by using MPC, we can achieve the input privacy that no intermediate values are reviewed to any individual server. And for the output privacy means that we can provide epsilon delta output privacy if all the information released also satisfy the same privacy guarantee. Okay. So actually our solution, we have the first of our solution that we consider a very simple case that we're just training on the global model, and we make the local model is frozen. So someone will say, okay, that would be very easy that we just apply the DP-SGD, the differential privacy SGD on the global model. Yeah, it's true, but here issue is here is that we said, in order to get a better privacy utility trade-off, normally we will apply use the privacy amplification techniques such as subsampling, but in WFL, there is a challenge because in WFL, normally we will do the data alignment, before we start the WFL training. So that means for all the clients, you will exactly know the data ordering because we already aligned here. But now that if you want to apply the permutation because you want to achieve the subsampling, that means every other clients will exactly know that the randomness. So that means this kind of information will not be a secret. Everyone knows it. Server knows it, and clients know it. So what do we do? That we have 2 protocols here to consider this case. So first, that we will still apply the ghosting mechanism with subsampling, but we will apply the secure shuffling in the server side to trying to prevent that random secret. And then another is that we use the banded matrix factorization, the BMF, and under this mechanism, we will not use the subsampling anymore, but we can still achieve almost the same performance compared to the Gaussian mechanism. So for the Gaussian mechanism with subsampling, so key area is still pretty straightforward. So first we have the forward pathing. But as I said, now we consider all the local models are frozen, so you can assume the local model is as a deterministic function. So that means that now we just pass all the data, each client pass all the data, to the local through the local model and the secret shares to the servers. So that means that, and on the server side, we just gather them together, and we get the edge, the here edge that is the intermediate result output from all the clients. So what we do is that at the beginning of every epoch, we just run one time the shuffling protocol, and we can get a new, we call it like the H prime. And what you do is just divide it by the H prime by multiple batches, and we just pass each batch into the global model, and we start the computing the gradients as we said before. Oh, sorry, I should mention that as the first step, once that we upload all the intermediate result, all the client just can leave the protocol because this is just a one-time communication. And so then the third step that we just do the standard SGD, DPSGD, right? And we get the gradients, we do the clipping, we add the Gaussian noise, we just update the global model parameters. So that's the thing. So for the banded matrix factorization is okay. So it's almost very similar to the Gaussian mechanism, but the only thing is that we need to compute the correlation matrix and to get a correlated noise added on the gradients at each step. Okay, so yeah, so the another solution, the third one is that we're trying to train both the global model and the local models, and what we do here is that we still utilize the banded matrix factorization mechanism, but we will introduce another technique. We're trying to extract the per sample gradients. So what we do is still same that we can have the forward passing we after at each the batch, and what we get is that we are not only just compute the gradients for the global model, we will also pass the partial gradients of the chosen local layers. Here is the phi I L would be the last layer or last two layer. So at the global side, that once we get the gradients, yeah, we will update the gradients and also get the G phi I, and we will pass it back to each client. But here the G phi I, we will note that it's the private gradients, and so it will not leak any information. And here I will stick with here is too much in the math here, but you can know that once we get a G phi I, we can extract the DH over D phi here, and we use it to update the local models here. And we can claim we have both input output privacy preserving from the theorems. So okay, so I will stop here, and if you have interest in my work, we can later, and I will show you both the experimental result and also the details. Thanks, everyone. Yeah.
Okay, thank you, speaker.